In this lecture, we'll discuss hypothesis testing as a generalized concept. As sub-aspects of the subject matter, we'll also discuss experimental structure, p-value, alpha value, symbolic notation, and how to determine the appropriate directionality. If this seems like a lot, it's because it is. Don't worry if not everything immediately makes sense. We'll continue to discuss this topic in later videos on the playlist and how it is applicable to differing methodologies. This subject is extremely important as it is the basis of all applied statistics. So the definition of hypothesis testing is thus. A statistical hypothesis is an assumption which may or may not be true. Hypothesis testing is the methodology utilized to test this assumption. Through this process, we either reject the null hypothesis or we fail to reject the null hypothesis. Now remember that we either reject the null hypothesis or we fail to reject the null hypothesis. So here's some common statistical methods which utilize hypothesis testing. Those are the ANOVA, the t-test, and the chi-square, and we'll explore each test in later videos. I wanted to talk about a little about structuring an experiment and the time allocation as it pertains to structuring experiments. So this is applicable to outside research outside of the classroom. But if you ever do find yourself in such a situation, or you're in the situation now and you're watching this video sort of just as a refresher, here's what I believe is the allocation of time as it relates to each step in experimental structuring. Pondering the purpose of an experiment probably takes about 5% of the time. Deciding on the appropriate test takes about 5% of the time. Describing the experimental parameters is about 5%. Collecting data related to the test while utilizing the experimental parameters throughout the process of such, I couldn't come up with a allocation for that because it'll differ depending on what your experiment entails. Cleaning and entering the data, this can be a mess depending on the data collection methodologies, et cetera. So that's about 40% of the time commitment as far as structuring an experiment is concerned. Performing the appropriate experimental methodologies, tests, et cetera. If you know what you're doing, that doesn't take very long. That's about 10% of the time. And then illustrating the data and writing conclusions, describing the methodologies, putting your findings together in a cohesive manner, which tells a story or paints a picture, depending on which metaphor you'd like to utilize. But what's very important as it relates to not only hypothesis testing, but performing experiments, applying methodologies, it's very important that you go into your data collection phase understanding what it is you're looking to prove or disprove. What is the purpose of your experiment? And the data that you're collecting, how can this data be structured and put into a particular methodology in which you can draw a conclusion? All right, so it's very important to go into the data collection phase, understanding that. Understand what you're asking, how you're going to prove or disprove the particular phenomenon which you're investigating, and what tests you're going to utilize for such. If you do that, the rest of the time commitment and application is a breeze. But if you go in not understanding what it is you're looking to determine and not understanding what tests will be useful to you throughout that process, you're going to have a really rough time because you're just going to have data which is all over the place, and you're going to have to hand it over to a methodologist or a statistician and say, here it is, find something, I'm kind of looking for this. Avoid that. Meet with your methodologists, meet with your biostatisticians, meet with your team of researchers prior to beginning the data collection phase. Make sure your structure of your experiment, whether it be a survey or whether you're going out on street corners with clipboards to collect data, make sure however you're structuring the data which you're collecting, make sure that structure is applicable to a particular statistical test, which suits the needs of your application. Now, with that out of the way, let's talk about determining confidence or deciding on confidence as it relates to hypothesis testing. All right, so we have our data, and now we want to apply a particular test, whatever test is appropriate, but we have to decide on the particular confidence or significance, as it were. So to do that, we have to determine the alpha value. Now, typically the alpha value, which is most commonly utilized throughout the field, it's typically 0.05. And alpha, that value, the way it's determined is it's 1 minus the confidence interval. Okay? So when statisticians speak of confidence, they are referring to confidence in this context. And when statisticians speak of significance, they're referring to significance in this context. So if we were to compare two means, and we could say one mean perhaps is larger than the other in determining that, we wouldn't say that we're this amount confident or that amount confident, or that our findings are significant or insignificant just based on those findings, just based on those calculations. There's an entire process which we apply as researchers, as statisticians, to make that determination. So, as far as deciding on confidence is concerned, the most common alpha value which is utilized is 0.05. It's an industry standard typically. There's other alpha values which you can utilize, but in the classroom and out and about, alpha is almost always going to be 0.05 unless you're operating under some sort of unique circumstances or some sort of unique research field, which would otherwise prohibit you from using 0.05 or has its own alpha value determined. On this slide, we talk about confidence. So remember, alpha is going to be 1 minus the confidence interval percentage as a decimal. So what is the corresponding alpha value in each instance above? Well, if we're speaking with 95% confidence interval, that would mean our alpha value would be 0.05 because it would be 1 minus 0.95. If we're operating with 90% confidence or 90% significance, it would be 1 minus 0.10. And if we were operating with 85% confidence or 85% significance, that would be 1 minus 0.85, which would give us a alpha value of 0.15. And I called myself here. If we're operating with a corresponding alpha value of 0.10, that would be 1 minus 0.90, which would give us a corresponding alpha value of 0.10. Okay? So confidence and significance when it comes to the field of statistics are synonymous. But we reach these figures by utilizing this calculation down here. So the definition of p-value. The p-value is the probability of the observed data given the null hypothesis is true. The p-value is a probability value, while the alpha level is pre-specified to determine whether we reject or fail to reject the null hypothesis. It describes the probability that the outcome occurs given the null hypothesis. So in summary, alpha is the parameter which we will set for our statistical test, and the p-value is the value in which we will utilize to assess the outcome of our test. So all statistical tests possess the corresponding hypothesis. We have the null hypothesis and the alternative hypothesis. Okay? So we have a null hypothesis and an alternative hypothesis if we're applying a statistical test, regardless as to what the methodology is, whether it be chi-square, ANOVA, t-test, etc. Each of those is going to have a null hypothesis and an alternative hypothesis. So let's talk about each. The null hypothesis can conceptually be remembered by assuming that this is the expected result in each case. So everybody knows this. Everybody knows that the sky is blue. Everybody knows that grass is green. Everybody knows that water is wet. Now, this isn't always true and depends on the type of test, but in most cases, the null hypothesis is, and if you're in statistics 101, this will probably be the case in every instance, but it's in most cases, a majority of cases, the null hypothesis can be conceptually remembered as the status quo expectation. The alternative hypothesis is the antithesis of its null counterpart. Its existence is the general assumption of the status quo being disrupted. So you're going to think, in this instance, all that I know and all in which I expected is wrong. Now, again, this isn't always true depending on test types, but in most cases, this is how the alternative hypothesis is defined and how it operates. Okay? So the pair is symbolically notated as such. When we state the null hypothesis symbolically, we state it as H subscript 0. And when we state the alternative hypothesis, we either state that as H subscript A or H subscript 1. Now, you're only really going to see this H subscript 0, H subscript A, or H subscript 1 within the classroom. Okay, we'll go over how to state findings for research in the APA format, and we'll go over research maybe in its own lecture. But if you're stating the null hypothesis and the alternative hypothesis and you're doing it symbolically, this is really only something you're going to encounter in academic exercises. When you're doing research and you're publishing research, you're not going to see in research H subscript 0, H subscript lowercase a, or H subscript 1. Just wanted to point that out. So here are the mechanisms of the test. We determine the alpha. Remember, the status quo assumption of alpha is typically 0.05. We determine the type of test that we're going to utilize. We perform the test, and we state our findings. All right? So with tests, we have to ask whether it's a one-tailed test, a two-tailed test, and if it is a one-tailed test, is it a left tail or a right tail? If it's left-tailed, we're thinking less than. And if it's greater, we're thinking right-tailed. Right-tailed is greater than. Two-tailed is we're looking for a significant change or a significant differentiation, regardless of the direction. And again, just sort of go with me here. We're going to get into a lot more detail as we do examples of application in later lectures in the playlist. But for the sake of just presenting this topic generally from a fundamental perspective, just hang with me here. This will make sense as we continue through. So for a two-tailed test with an alpha value of 0.05, this is what our rejection regions would resemble. And here we have actually in every instance that we'll be demonstrating in these slides, we have a normal distribution. Obviously, this isn't always going to be the case. Your data is not always going to be normally distributed. But just for the sake of keeping things simple and illustrating the concept, I used a normal distribution in each instance. So these are our Z values down here. And we have a 95% confidence and a 5.05 alpha. So that means our tals are going to be one on the left, one on the right, and we're going to divide alpha in half. So 2.5% here and 2.5% here. And if we were to sum this entire probability distribution, it will come to 100%, as you can see. Okay, why this is will become evident as we go through the playlist. If we have a one-tailed test, a one-tailed test to the right, that would be greater than. Alpha is 0.05, 95% confidence interval. And here we are, 5%. 95% plus 5% is 100%. Okay? And here is one tail to the left, 95% confidence. Alpha is 0.05. So let's just do a couple application examples just to demonstrate, just to sort of demonstrate the concept. Generally, that is. All right, so this is an example of a one-tailed t-test to the right. A factory employee believes that the cakes produced within his factory are being manufactured with excess amounts of corn syrup, thus altering the taste. 10 cakes were sampled from the most recent batch and tested for corn syrup composition. Typically, each cake should comprise of 20% corn syrup. Utilizing a 95% confidence interval, can we assume that the new batch of cakes contains more than a 20% proportion of corn syrup? So I'm going to show you what the key terms and phrases are in this word problem example that you need to be aware of as you go through these steps in your own research. So we see 95% confidence interval. So as you recall, 1 minus the confidence interval as a decimal is the corresponding alpha value. So our corresponding alpha value in this case is going to be 0.05. More than or greater than indicates a one-tailed test to the right. So we're looking at a situation, if we were to draw this out generally, that would resemble this illustration here. So our data set, our observations, are up top, as you can see there in the braces. N equals 10 because we have 10 observations. Our confidence interval is 0.95. Our alpha value is 0.05, and the mean is 0.2. The mean was given to us here. And though it's not within this problem here, our 10 samples are here. So N equals 10. So we're going to state the null hypothesis and we're going to state the alternative hypothesis. The null hypothesis in this instance is mu equals 0.2. And the alternative hypothesis is mu is greater than 0.2. And mu is the symbolic notation for mean. And each hypothesis test, depending on the methodology which is being applied, is going to have a different way in which it's stated. So H subscript 0 and H subscript A will remain the same, but everything that happens over here and over here is going to differ depending on the test which you're applying and other sub-attributes of the test itself. So if you needed assistance with that as it pertains to what you'll be placing to the right of H subscript A or H subscript 0 for your research within the classroom or otherwise, just Google or use another search engine, hypothesis test or symbolic notation for hypothesis test for whatever the methodology is. So hypothesis test for chi-square, hypothesis test for ANOVA, hypothesis test for t-test. And then you'll be able to get the appropriate symbolic notation for the right side of the null and the right side of the alternative. So if we're doing our results and we're reporting them within an academic setting, academic meaning in the classroom, not as publishable research, which we'll go into in later slides in a later lecture, with a p-value of 0.002 0.02572 less than 0.05. This is our alpha value right here, okay? This is our p-value that we received from applying the test, and we'll go into how to derive these results in later lectures. But if our p-value is less than our alpha value, not less than or equal to, if our p-value is less than our alpha value, we reject the null hypothesis. So with a p-value of 0.002572, which is less than our alpha value, and a corresponding t-value of this is, you'll get this derived from the output of the test application, at a 95% confidence interval, or with 95% significance. Remember, it's because 1 minus 0.95 is our corresponding alpha value. At 95% confidence, or at 95% significance, we will reject the null hypothesis. And as such, we assume that the cakes which are being produced contain an excess amount of corn syrup. Let's do a two-tout example. A new type of gasoline has been synthesized by a company that specializes in green energy solutions. The same fuel type, when synthesized traditionally, typically provides coupe-class vehicles with a mean of 25.6 miles per gallon. Company statisticians were provided with a test sample of 8 cars which utilized the new fuel type. This sample of vehicles utilized the fuel at a mean rate of 23.2 miles per gallon with a sample standard deviation of 5 miles per gallon. Can it be assumed at a 95% confidence interval that vehicle performance significantly differs when the new fuel type is utilized? All right, so there's a few things going on here. Let's make sure we figure out what is important for our application. So as you can see, we have a 95% confidence interval, which again corresponds with an alpha value of 0.05. We're wondering if the performance significantly differs, not whether it's greater than or less than. We don't want to know whether there's a greater miles per gallon or a less than or a significantly less miles per gallon. We're interested in whether or not performance significantly differs. So this phrase signifies a two-tout test. It looks like we have our mean, and we're going to receive samples from the 8 cars which were tested. So here we have our sample size, 8 samples, our sample standard deviation, that would be derived from our samples, okay? We're not going to go into it here. We have our mean, that's the mean from our samples, okay? So we have the mean from our samples, the standard deviation from our samples, the number of samples. These weren't given in the word problem, but we're going to assume that you've derived these yourself, these two values here. Our confidence interval is 0.95, and our alpha value is 0.05, because remember, 1 minus 0.95 is 0.05. So let's state our null hypothesis, mu equals 25.6, and let's state our alternative hypothesis. Mu does not equal 25.6. And remember, mu is the symbolic notation for mean. So in this case, we receive a p-value of 0.2167 from the application of methodology. And we'll go into how to do this. But in this case, we're just going to assume that we applied our methodology and our outcome, our p, is 0.2167, which is greater than 0.05 in this case. Remember, greater than or less than, not equal to, okay? So 0.2167 is greater than 0.05, and our corresponding t-value is negative 1.3576. I'm often asked, is a negative t-value, if we get a negative t-value, is that accurate? Did I do something wrong? The t-value can be negative. And this t-value corresponds with this p-value here. We have to state it in our results. But in any event, because our p-value is greater than our alpha value, we will fail to reject the null hypothesis. If our p-value is less than our alpha value, we will reject the null hypothesis. But in this case, it's greater than our alpha value. Alpha value is 0.05. Our p-value is 0.2167. So we fail to reject the null hypothesis. Therefore, we cannot conclude that at a 95% confidence interval, or with 95% significance, that vehicle performance differs depending on utilization of fuel type. So something very important to remember as it relates to p-value and testing, if the p is low, the null must go. If you take nothing else away from this particular lecture, please take away, if the p is low, the null must go. If you're in a statistics course with your friends, or if you're meeting with other methodologists, tell them, if the p is low, the null must go. Everyone in research should have this motto memorized. It's very useful for any application of hypothesis testing, okay? If the p is low, the null must go. I won't say it again. So with that, I know we covered this topic, which is a very specific topic in a very generalized and broad-based manner, but we're going to get into the application and the specificity of the application in later lectures in this playlist. If you were able to learn anything today, or if you found this helpful, I would encourage you to please like and subscribe. It would mean a lot. It would help me out. And I wish you the very best, whether you're in a stat course or whether you're doing your own research. As it relates to research, remember to structure your experiment before you go out and collect the data. It'll be incredibly helpful to you later on, believe me. With that, I hope you have a wonderful rest of the day. Thanks for stopping by. Thanks for sticking around, and take care.